Okay, so 2 examples for this. Let's have the first one. I think we did these in class. I'm pretty sure we redo them now so you can see it again. It's too bad we missed out so much time, and we had a nice momentum going, I thought, but you know, there's no point in trying to panic or rush and do too much. We're going to just continue where we did and try to get that back now for the next 5 weeks or so, 4 weeks. Okay, so let's do an example. Suppose we have a sample yi is uniform and 0, say, theta, where for is the sample. So I equals 1 to n iid. Okay, so let's find an MVUE for theta. Find an MVUE for theta. Okay, so we'll start. So the solution is find a sufficient statistic using the factorization criterion and find a function of it that's unbiased. This will be an MVUE. Okay. Another piece of paper. All right, so remember the factorization criterion. We have to factor the likelihoods. So we want to find a sufficient statistic first for it. So we know that L theta y is equal to the product 1 to n. All right, what is the density of each yi is 1 over theta, but it also must be between 0 and theta, so I'll write it like this: 1, 0 less than yi less than theta, something like that. Okay, that I can now take that product, the constant comes out, so I get 1 over theta to the n. And I can write this like the maximum order statistic has to be less than theta, and the minimum has to be greater than 0. So I'll write it like this: 1 yn less than theta, and also 1, because if either of these aren't true, that will make the whole thing 0, y1 greater than 0. And you see here, you have your yn and theta. Here you have other stuff, but no theta. So by FC, y, and now I'll write it like this: yn is sufficient. So I write a big yn is sufficient for theta. Okay, so now I want to find an unbiased estimator, a function of y of the nth order statistic that is unbiased for theta, and I'm there. This part's easier. The harder part is identifying the sufficient statistic. This should not be too bad. I need to know the expected value of yn, and then hopefully there is a way to do this. But so let's compute it again. So we know, so recall the density of the nth order statistic, y is equal to n CDF y n minus 1 times the density function, which in this case is n. This would be y over theta to the n minus 1, right? And now this is going to be 1 over theta. and 1. Let's see. Yeah, this is the PDF, so 1, it has to be between 0 and theta. Okay, very good. So that can be simplified a little, but we'll leave it. And so E of yn, expected value, is just the integral 0 to theta. That takes care of the indicator function. And I'll put the rest of this stuff in here with another y. So it's y n y over theta to the n minus 1 over theta dy, which is just equal to the, I get theta to the n comes outside, the n comes outside, so I just have n over theta to the n, integral 0 to theta, y to the n, dy, y to the n dy, that's y to the n plus 1 over n plus 1. So I get n over theta to the n times y to the n plus 1 over n plus 1. So I get theta to the n plus 1 over n plus 1, which equals theta n over n plus 1 theta. So n plus 1 over n times the nth order statistic is unbiased, right? If I multiply this by this, I will get theta. So is an MVUE for theta. It's unbiased, and it's a function of a sufficient statistic, since it's unbiased, and a function of a sufficient stat. Maybe one more, and this will conclude the lecture 0. All right, so example 2. Suppose we have yi is normal, mu1. Again, I equal 1 to NIID. Let's find an MVUE for mu. Okay, well, same thing. So we use factorization criteria to get the sufficient statistic. You might remember a sufficient statistic, actually. We can do it, though, one step. So we have L mu given y, write it like that, is equal to product 1 to n, and what is it again here? So we have 1 over square root 2 pi exp minus 1/2 yi minus mu squared, right? Yep. Okay, let's multiply that out. I get equals 2 pi to the minus n over 2. Just clean that up a little. And now I have exp minus 1/2 sum 1 to n of this yi minus mu squared. Let me, while I'm at it, yi squared minus 2 mu yi plus mu squared. Yeah? Yeah. Okay. Looks promising. Let's just now break this into 2 pieces so I can take this and write this. And by the way, notice no indicator functions because this is defined on the real numbers. So this is that, and I will take this one out separately, I think. Yeah, oh, I need the mu to go with this one. So this is the one I want out separately. So I have exp minus 1/2 sum yi squared and exp minus a half times this, right? So I have the sum here, so minus a half, and then sum minus 2 mu yi plus mu squared. All right, well this one I can write, so this I can say, this does not involve mu, right? But it does involve the sample outside of the sufficient statistic, and this is just a function of mu and a sufficient statistic, because I can take the minus 2 mu outside here. So this is equal to, this piece is equal to exp. Let's do it. So I have mu. If I take this outside, right, I get a positive mu times the sum here. So I get n mu y bar. And here I have, I don't have this anymore, so I have the mu squared can come outside. So I get actually n mu squared, so I get minus 1/2 n mu squared, right? Something like that. So we see, so y bar is sufficient for mu, and we know, and since EY bar is equal to mu, we see that right in the first week of class or so. Y bar, we don't need to mess with it and find some function of it that's unbiased. It already is unbiased, is an MVUE for mu. Okay, thanks. Next lecture is on the method of moments.